Let's talk about writing proofs in trigonometry. Proofs are how mathematicians talk to each other. Well, not really, but in a way they are how we share fundamental mathematical ideas that, once established, can be used over and over. After something has been proved, it is unquestionable, and anyone can use the result to do bigger and harder problems without first having to stop to establish each piece. The trigonometric identity sine squared plus cosine squared equals 1 should be familiar to you and serves as a good example of why proofs are important. If I am asked to demonstrate that 1 plus cotangent squared equals cosecant squared, I can start with the known identity sine squared plus cosine squared equals 1 because that one has already been established. Imagine if you had to prove that one first each time you wanted to use it. Something you should know before we start is that when you see someone demonstrate any kind of proof, chances are that they know exactly what each next line is going to look like. They have probably worked out the steps beforehand and are just showing you what those steps are. In reality, writing proofs is much messier than that. In another video, I'll show you what I mean by working through a proof I haven't prepared in advance. There are multiple ways to write proofs. In this video, I'll show you how to prove a trigonometric identity the way I require my students to do it. Your instructor might want you to do it a different way. If no particular method is dictated, then this technique will almost always work. Since this is the first time for most students that they've had to write a proof on their own, I feel it's best to give you one strategy so that you can focus on the logic and the importance of the details. As a student, I always felt like writing proofs was some mysterious skill that you had to figure out on your own. That's because there are so many different ways to do it. This is just one, but it is highly structured and should serve you well in most cases. Let's prove the identity tan theta over secant theta equals sine of theta. This is a very easy proof, but it will demonstrate the process. Then we'll do some harder ones so that you have some other models. Begin by writing out what it is you're going to prove. Tangent of theta over secant of theta equals sine of theta. This is a statement that you are making a claim and that what follows will demonstrate that your claim is true. Some mathematicians and some instructors may have you write required to prove or RTP to the left of this statement. That helps establish that it is a claim rather than an assumption, and that there is more to follow the initial statement. Adding that is not wrong, so I'll leave it. Now we'll select one side of the identity and show that it is equivalent to the other side. This is where a lot of people get lost. Since you are trying to prove that the two sides are equal, the one thing you must never do is say that they are equal. You have to demonstrate that they are equal, using logic and algebra. The side that you choose is up to you, but it is usually easier to do the proof if you start with the more complex-looking side. That's because there's more on that side to work with. So we'll begin with that. I will choose the left-hand side of this identity and show that it is equivalent to the right-hand side. Since I am using this to communicate with others, even if it is just my instructor, I must be very clear about each thing I write and what role it plays in the process. To that end, you must write LHS, which stands for left-hand side, at the beginning of your proof. Some instructors may not require this step, but I do. Next to LHS, I will state what the left-hand side is, namely tangent of theta over secant of theta. I note that these are equal since it is simply a statement of fact that the left-hand side of my identity, which was given to me to prove, is in fact tangent of theta over secant of theta. The rest is up to me. I have to show that this expression is equal to another expression, which is equal to a third, and so on, until I have found a way to write it so that it looks like the right-hand side. To do that, I'm going to use a series of trigonometric identities that have already been proved or which I've been told that I can use. For example, algebraically, I can write tangent of theta over secant of theta as tangent of theta times 1 over secant of theta. All I've done is use a little bit of algebra to write this expression as a product instead of a quotient. Now I'll use some trigonometric identities. One is that tangent of theta can be written as sine of theta over cosine of theta. Another is that secant of theta is 1 over cosine. More importantly for me, 1 over secant is cosine. So 1 over secant of theta can be written as cosine of theta. Now we can make the observation that the cosines can be canceled. After that, when I tidy up my work, I just have sine of theta. Well, this is exactly what I was trying to prove, that tangent of theta over secant of theta was equal to the sine of theta. And I've done that now, not by making any assumptions, but by using some previous results and showing algebraically and logically that the expression tangent of theta over secant of theta is equivalent to the expression the sine of theta. There's one last step here. At the beginning, I wrote LHS for left-hand side. At the end, I'm going to write that this is equal to RHS, which stands for right-hand side. So ultimately, what I've shown is that the left-hand side is equal to the right-hand side. And there are several steps in between, but each one is equal to the one before. And that's the sort of thread of logic that we want to use in these. As I said before, there are multiple other ways to write proofs, but trigonometric proofs are easy in a way in that you can always use this strategy to show one side of your identity is equal to, algebraically, some other expression. And then you can just continue playing with those expressions algebraically and using trigonometric identities that you already know to rewrite the expression until it looks the way you need it to look. It sounds simple, and sometimes it is, and sometimes it's more complex. Let's try another one so that you can see what I mean. My instructions might look something like this. Verify the identity cotangent of x times secant of x all over cosecant of x equals 1. The left-hand side looks considerably more complex, so I will start with that side again and show that it is equivalent to the right-hand side by demonstrating several intermediate algebraic steps. We have to remember that we are required to prove, although for some people that step may be optional, we are required to prove that cotangent of x times secant of x all over cosecant of x is equal to 1. And then when we begin, you may also want to write proof to show that you're about to prove this statement. Now let's write left-hand side equals, and we'll rewrite the left-hand side. Cotangent of x times secant of x all over cosecant of x. Notice that I have not done anything in this step to change the left-hand side. I have not done my first algebraic logical step. I have simply rewritten the left-hand side. This is important because you're establishing a starting point. It's really tempting, especially with ones that seem like they're going to be easy, to dive in and start rewriting things. But your first step should always be just to rewrite one side or the other of the identity. Now that I've done that, I can start playing around with it. I'm going to start the way I did the last time by writing this quotient as the product of the numerator, cotangent of x, times the secant of x, times 1 over the denominator, cosecant of x. I've simply changed the form that this expression takes. Now I can start playing around with each of the three pieces here. The cotangent of x can be written as cosine of x over sine of x. Secant of x can be written as 1 over cosine of x. And 1 over cosecant of x is sine of x. Now I can see that sine of x over sine of x will cancel, and cosine of x over cosine of x will cancel. And everything has canceled now, and the result, therefore, is 1. Well, that's exactly what I wanted. The right-hand side of the identity that I'm trying to prove is 1. So at this point, I can just say that that equals the right-hand side. And I'm done. These two examples were very similar in the strategy used. In the next video, I'll discuss a few other strategies, and we'll do some examples using those.